Okay, so I've been interested in the so-called quantum state preparation problem, which is an echo. Okay, thank you. So, which is how to prepare a given quantum state, say an eigenstate of a Hamiltonian, on a quantum computer. You still want me to move over? Or it's okay now?
It's okay.
It's okay. Yeah, so, and why you might want to do this, well, you could, for example, once you have the state, you could, say, compute correlation functions in this state, which would be hard to calculate otherwise, especially for very large systems. And then you ask, so what would be a interesting eigenstate to look at, for what Hamiltonian? And coming from an integrable community, for me, an attractive candidate would be a beta state, that is an exact eigenstate of an integrable Hamiltonian. Because on the one hand, these states are better understood than some eigenstates of some generic Hamiltonian. And also, these states are very not true. So the goal of, the main goal of today's talk is to describe an algorithm for preparing beta states of the Heisenberg quantum spin chain. And this is work I did recently with my student, David, in the archive. So here's an outline of the talk. So as a warm-up, I'll describe how to prepare Dicke states. So these are kind of baby versions of beta states, which are actually of interest independently, quantum information. Then I'll give a brief review of beta ansatz. And then I'll describe the generalization of the Dicke state circuit to that of beta states. And then as a application of that circuit is I'll describe a way to get beta roots using a variation of quantum eigenstates. And then I'll end with an output. Okay, so let's begin with Dicke states. So roughly speaking, Dicke state is a completely symmetric n-qubit state of ones and zeros. So here, 0 is this, as usual, 1, 0, and 1 is 0, 1. And so the k here, so D is for Dicke, the k tells the number of ones in the state, and then in the n here is the total number of qubits. Okay, so the number of zeros is n. So as an example, for D42, so these are 4-qubit states with 2 ones. So it's all possible superpositions of 2 ones and 2 zeros, and with coefficients 1. And here, the notation here, this just means tensor products. And it's there's 6 terms. I normalize with 1 over root 6. So, so this state, you can think of it as starting with the state of all n qubits in 0 state, and then applying k times the spin lowering operator. So spin lowering operator, S minus, is Sx minus I Sy. And then the spin operator is S. So it could be Sx, Y, or Z. Is just the sum of the spin operators at each site from 1 to n. And for spin a half, each of these spin operators is just 1/2 the Pauli matrices. And so here sigma x is x, and sigma y is y. Okay, so this is so up to normalization. This gives you the Dicke state with k ones. And it turns out these are already a bit interesting from the point of view of Hamiltonians. But these are exact ground states of the ferromagnetic Heisenberg model, which has this Hamiltonian, and also so-called Lipkin-Meshkov-Glick Hamiltonians. here. So one can ask, how can I prepare these states on a quantum computer? So unfortunately, one cannot simply implement this definition on a quantum computer because this S minus operator is not unitary. So you have to do something a little bit more clever. And so instead, one can start with a simple, I'll call it a reference state, which is just a product state, which has the requisite number of ones. So it has k ones and the rest are zeros, but it's just one product state, no linear combination. And then what we're looking for is some unitary operator U, which will take this simple state into the Dicke state. So I want to call this operator the Dicke operator. And as I said, I want it to be unitary so that I can implement it on my quantum computer. And also, for simplicity, we're going to assume that it doesn't depend on K. Okay, so the only K dependence is in this reference state. So there was, so one way to do it is, was found by Bertschy and Eidenbenz back in 2019. And their idea is to exploit recursion. So let me explain. So on the example, so coming back to this example of D42 that I showed earlier, you notice that these three guys, they all end in 0, so I can factor out the 0. And then what's left is also a Dicke state, okay, with still 2 1s, because I just took out a 0. And now these three guys all end in 1. I can factor it out. And what's left is again a Dicke state, but with 1 less 1. So if you mind the normalization, the coefficients, you see that this guy is a D32 and this guy here is a D31. And this is true in general, not just for this example. And it's very easy to convince yourself that I can write dnk in terms of dn1. So 1 less qubit, okay, but here k ones and here k minus 1 ones because I took out a 1 already. And these are the right coefficients. Okay, so what I'd like to do now is exploit this recursion to get recursion on the Dicke operator. So I'm going to replace the Dicke states in terms of U on both sides. Okay, and because we assume that these U's don't depend on K, I can bring it outside of the two terms. So here the K's are different. Okay, and then what's left is this, and I'm going to define a new operator W, which when acting on my reference state will produce these two terms. So, so let me repeat that on the next slide. Oh, sorry. And I want to insist that this W be unitary, like my Dicke's operator. And I'm also going to insist that it doesn't depend on the value of K. So yeah, here's the same thing again on the other slide. Okay. And so, so now I have a recursion that U for n qubits is related to the one with n minus 1 qubits. But then there's this kind of correction for the W. But now you see, I can now telescope this recursion. And I see that the U, the thing I'm looking for, is given just by a product of W's. This is an ordered product. So this symbol here means I should order the terms from left to right. It's here. So it suffices to construct operator W that does this job, because once I have W, then from here I get my Dicke up. Question so far. Okay, so how to construct the W's? Well, the strategy will be to introduce some simpler operators I'll call I, which carry now instead of 1 index M, it'll carry 2 indices, M and L, such that when L, that index is the same as this one, so when L prime is L, it does the job of W. But if the index L prime is less than L, it doesn't do anything to the reference state, it just leaves it alone. I remind you that the reference state is this simple product state, which has the right number of ones and zeros as my Dicke state. So the point is that these operators should perform the job of W for a fixed value of L. That's what these operators do. And furthermore, if I act when L prime is bigger than L, it shouldn't do anything to this because this guy here is already what I want. So if I act again with another I, it shouldn't disturb it. So in other words, I'm going to order these I operators so that they don't interfere with each other. And then it's pretty easy to convince yourself that now the W, the thing I'm looking for, will just be given by an order product of these I operators. And now the product is from right to left, again indicated by this. So now we boil down the problem to constructing these I operators. If I have the I's, then from here I get the W's, and from W's we get. And then it turns out these I's are very simple operators. Let me step through it. So again, for when this index is the same as this one, it should do the job of W. And I remind you that the reference states are given here, has the right number of ones and zeros, product state. And by definition, this W operator does this. Okay, so my operator should do this. And it looks complicated, but actually, if you stare at it for a minute, you'll see that it's very simple. If you look here, we have L1s. I've written them here, and then I have the rest are zeros. And this state here is exactly the same as this state here. Right? I have L1s, and then I have the rest zeros. And the state here is almost the same, except the guys in blue are swapped. So what was a 1 is now a 0, and what is a 0 is now a 1. So, so really, this I operator should only just act on the 3 qubits, the ones I've labeled 0, L minus 1, and L. This is Dicke conventions. And what it does, this state stays the same, except it picks up a coefficient. And in this guy, where the qubit 0 and L are swapped, has a different coefficient. Okay, so if I construct that, then I'm in business. So let's define, so this is going to be a kind of rotation. So let's define a rotation angle such that cosine theta over 2 is equal to this, and minus sine theta over 2 is equal to this. So again, these are the coefficients. Yeah, so in the pre-seminar, I explained how this circuit exactly does this transformation. So if you were here for the pre-seminar, that's exactly what I described. So here, this is a control knot. This is a double controlled rotation, where this is the rotation operator. This is another control. So yeah, this is a 5-minute calculation. And so that's it. So now we have all the ingredients. And then if you look at the circuit size, it turns out to be of order k times n minus k. So it's linear in the number of qubits. So you can easily code this on Qiskit. So for example, this D42, so this is a full circuit. So this guy here is my reference state. So I have 2 1s, which I get by acting with knots. These are all start off state 0. And then I apply my W's, W4, W3, W2, and each of them is made up of these I gates. And yeah, and that's it. So questions about any of that? Okay. I should say that I'd like to advertise another construction which is related that we recently found, which is sequential preparation based on matrix product state representation, Dicke states.
There's a notion that this is a minimal, algorithm to obtain the states by some measure.
It's not, no. In fact, I'll comment that in a minute. I mean, it's efficient, but it's not the most efficient.
So in all algorithms, we sometimes work with these constructions called block encodings, where you can kind of encode a non-unitary matrix into the unitary operator on a bigger space.
Mhm.
Since you mentioned that this S minus operator is not permission,
Mm.
I was wondering maybe do you know if people have used these block encodings to
Yeah, I'm not aware of it, but that could be really interesting.
I like don't take my promise on this, but it might be possible to get get a complexity that's better than linear in the number of qubits.
That would be awesome.
But that's just my intuition.
Yeah, no, that would be awesome.
Okay.
Yeah, I should
So this-
definitely look into
This
this.
technique is also known as qubitization, which has been used in a slightly different context. But if you want to know more, then that's the term to look for.
Mhm. Okay, maybe we can talk a little bit
Of
after.
course, yeah.
Great. Yeah, so this is yet another way. Oh, now it works. Okay, great. So, thank you. Okay, so any n qubit state, and particularly the Dicke state, can be written in this way. So here M is just a computational basis for n qubits. So M1 to Mn, where these Mi's are either 0 and 1. So here, yeah, these are just qubits. And we're going to refer to now this as a physical space. And the coefficients, so I'm writing, these are just C numbers, can be written in this way. So this is so these operators A turns out K plus 1 by K plus 1 matrices, where K here is the same K as the K in the Dicke state. And in these states with the underscore 0 and K, these are computational basis states, J for a K plus 1 level system. So the index J runs from 0 to K now. So this is a qubit. And we're going to refer to this as the bond space. The bond dimension is K plus 1. And what we found is exact formulas for these matrices. And they're very simple. They involve just binomial coefficients. And they're quasi-diagonal. So when M can be, again, either 0 or 1. So when M is 0, this is just a diagonal matrix. And when M is 1, it's just the next diagonal over. And it turns out that this is the minimal bond dimension to make a Dicke state. And it's exact. Yeah, so people have known for a long time exact MPS representations for, say, a KLT state, but they're bond dimension 2. In GHZ, again, bond dimension 2. But here, the bond dimension can be anything, a K. For any K, it's K plus, bond dimension is K plus 1. And moreover, these have been engineered so that the A matrices are canonical, satisfy this condition. And so that means that one can define an operator U, which acting on a qubit and on a qubit does this job. And because they're canonical, this U can be made unitary. And so you can use this U to prepare the states sequentially. So the idea, again, this is an old story, but you make just an order product of these UIs. And because the A's is an MPS for the Dicke state, when I act with this curly U on this state, I get the Dicke state that I want, and also the qubit is in the state K. And note that they're decoupled, so this gives you a deterministic way of preparing the Dicke state. And it's not difficult to come up with a circuit that does this job. So in the same kind of spirit as we did before, we can write this U in terms of some simpler operators. Again, I'll call them I, which should do the job that we need when so they depend on an extra index L. So when L is J, does the job that we want, and when L is less than J, it doesn't do anything. And this turns out to be this simple circuit that does that. So this angle is in terms of the coefficients appearing in the MPS representation. And these are gates that just raise the state of the qubit from J to J plus 1, this one, and this one lowers it from J to J minus 1. And so if I represent this U operator in this way, then this guy is just a product of them. So this is the circuit. And well, yeah, this on the reference state will give you the Dicke state. And one can compute the circuit size, and again, it's linear in N.
So only these big circles are controls?
Yeah, this is a control. Because it yeah, it's yeah, it's a control, but control on 0. Yeah,
One k is equal n over 2, so it's basically quadratic.
it's yes, it's quadratic. Yeah, that's the worst case.
Okay. And maybe like immediate follow-up question is why? So there exists another way to prepare the state with short transform, which is linear on that, and not quadratic. And then
Even for k is n over 2.
Yeah. So and I guess I'm just wondering why this way somehow is the one which is maybe better. I guess it might be better for generalizing this better.
Well, I don't know. I don't know this other way.
Okay.
Tell me about it.
Yes. Okay.
Yeah, and I should say that so this you can code in circ. The circ can do qubits, and because you do need one qubit in the circuit. So yeah, you can code it in circ and it works. So there's yet other approaches. So I didn't know that one. So there's a group in Delft that have used quantum phase estimation. There's a group here and has a recent paper on this. There's also a circuit by these guys, which I think is constant depth. And then there's I learned about some work that's going to appear soon from Maryland. So yeah, so a lot of people are interested in this.
Sorry, could you go back one slide?
Yeah.
Show the circuit again. So it is like this cascade, but where does the factor of k appear?
Factor of k.
You have the 3k improved. Is it in the implementation of each of these control, like of these kind of plates that you have across new circuits?
So to count the size.
Oh, I see. It is. I see. It is the gate that you have there with this red and blue box. It's a sequence of. Is that like k?
Yeah, and actually I lied a little bit because you don't need all k plus 1 here. You can actually to make it smaller, but yeah, if you do it carefully, this is better.
So the result of Piroli and co-workers, that's using intermediate measurements, I guess.
Exactly, intermediate measurements, feed-forward operations. Yeah. Yeah. And actually, one can generalize the notion of qubit of Dicke states. So instead of spin a half, right? We had this something like this, right? So instead of this being spin a half spins, one can go to arbitrary spin. And so it's kind of generalized Dicke states, and we worked out a circuit for those. Also, instead of qubits, one can also go to D-level systems. So then instead of SU2, then it's SUD Dicke states, and we worked out a circuit for that, and even Q deformations. Okay, so now I'd like to generalize the story to beta states. So let me begin with a brief review of beta ansatz. So So apologies to the experts. So I'm going to focus for simplicity on the so-called closed, so periodic boundary conditions, isotropic, so SU2 invariant or XXX, spin-a-half Heisenberg quantum spin chain. So, so this is a deceptively simple model of magnetism put forward by Heisenberg at the dawn of quantum mechanics. And the idea is you have L spin-a-half spins or qubits arranged in a circle, and each spin interacts isotropically with its nearest neighbor. And so this is the Hamiltonian. So, so when here n is equal to L, I have this sigma L plus 1, which you identify as sigma 1. So this puts implements periodic boundary conditions. And then sigma n means at site n, it's polymatrix sigma, otherwise it's identity. Yeah, so these are the three polymatrices. And this boldface 1 is the 2x2 identity matrix. And this dot here means I should, it's just a sigma n j, sigma n plus 1 j, where j runs from 1 to 3, and I sum. So this is a 2 to the L by 2 to the L matrix. And well, it's one of the most fundamental models in theoretical physics. It appears everywhere, has connection with conformal field theory, with ADS-CFT. It can be realized experimentally. And what one can ask, for example, what are the eigenvalues and eigenvectors of this Hamiltonian? But if you just want to put it on Mathematica, you can't go very far, right? Because these matrices are growing in size exponentially fast. But remarkably, just a few years after Heisenberg proposed the model, Bethe found a remarkable solution, which is now known as coordinate Bethe ansatz. And he reduced the problem to solving a system of polynomial equations. These equations are known as Bethe equations. Now, you can't do this for any model, not even in one dimension. It's only special models can be solved in this way. And those are the ones that are known as quantum integrable. And the basic idea there is that we have many conserved commuting quantities. So for example, quantity I'll call H3, which involves next nearest neighbor interaction. So cross product of these two and then dotted into sigma n. Turns out this commutes with the Heisenberg Hamiltonian. And one can also write an H4, an H5, so on. So this is quite special. And it turns out those models can be solved in the way I'm going to, along the lines of what I want to explain for this model. So the basic idea of the solution is that the eigenvectors are multi-particle or so-called magnon states. So the ground state is the one with no magnons or no particles. And this is very simple. It's just the state with all spins up or all qubits in the state 0. So this is an eigenstate of the Hamiltonian, and we've chosen the Hamiltonian such that it has eigenvalue 0. Okay, so for one particle state, the idea is that you'll flip one of these spins, so say at position X, and then you make a superposition of such states, and you weigh them by phase e to the ikx. I'll call that state psi k. And it turns out that these are eigenstates of the Heisenberg Hamiltonian. The eigenvalue I'll call little e of k is given by this expression. It'll appear in future slides, so I'll put a box around it. So we can regard this as the one particle energy. Now, this isn't true for any value of k. It's true only for special values of k, namely those that satisfy this condition. So if this is true, then we have an eigenstate and we have an eigenvalue. Okay, then now let's look at two particle states. So it gets much more complicated. So now we're going to flip two spins, say at position x1 and at position x2. We're going to put some coefficient, explain in a minute, and we'll sum over all x1 and x2. So the coefficient involves this little s, which is a function of two numbers, k1 and k prime, very simple expression. And if I look at the ratio of these two little s's, I get denoted as big S, which you can regard as the two particle S matrix for the scattering of these two magnons, of these two particles on the line. And notice that in addition to this little s, we also have a phase e to the I k1 x1 and k2 x2. And this guy here is exactly the same, except the k1 and k2 are permuted and there's a relative minus sign. Okay, so it turns out this guy is an eigenstate of the Heisenberg Hamiltonian, and the eigenvalues are just the sums of the one particle energies for these now two particles. Again, not true for any k1 and k2, but only for those that satisfy this set of equations. So again, if we can solve this, then we have an eigenvector and we have an eigenvalue. Okay, and then finally the M particle state looks again a little bit scary, but it's just a generalization. So now we're going to flip M spins at positions x1 to xm. We're going to put coefficient and then sum over all possible values of the x's. So this coefficient here, this A, is given by a product of these little s's on the previous slide. I have also, there's a sum over all permutations now of 1 to m and sigmas, and this epsilon sigma is the signature of the permutation, so it can be plus or minus. And here I have the k's can be permuted, this sigma j. And now this state is an eigenstate of the Hamiltonian, where the eigenvalues is the sum of the one particle energies, provided that these k's satisfy this set of m equations. And these are known as beta equations, and this state here is the beta state. And well, if we make change of variables, so we go from k to u, defined this way, and we define uj as u of kj, then these equations here can be rewritten this way. And if I cross multiply, you see that these are just polynomial equations for these u's. So a system of m polynomial equations or m unknowns, these uj's. If you can solve that, then you're done. You have your eigenvalues and you have your. So that's oh, one more thing. So just to yeah, it turns out this model has SU2 symmetry. And so it turns out that the degeneracy is given by in terms of ln m in this way. And also the m, the number of overturned spins, can be restricted to be less than or equal to L over 2. Yeah, to show you how this works, if I take a chain of length 4, L equals 4, then according to here, m can be either 0, 1, or 2. And I can summarize results in the table. So when m is 0, I have no beta roots, right? That's what it means. The energy we set in the 0 particle sector is 0. And the degeneracy, according to this formula, is 4 minus 0 plus 1 is 5. So this eigenvalue 0 will appear 5 times. When m equals 1, turns out there's 3 solutions of the beta equations that u can be either a half, minus a half, or 0. And then the energy formula would give me these corresponding energies, and the degeneracies of these are 4 minus 2 plus 1, which is 3. And finally, for the maximum value m equal 2, it turns out there's 2 solutions of the beta equations. Here's one of them, and here's the other one. Corresponding energies are here, and these are singlets. Degeneracy is 1. And so if you add up numbers in this column, you get 16, which is 2 to the 4, which is 2 to the L. So we see that the beta ansatz is complete in the sense that it's giving us all the eigenvalues of the Hamiltonian, and in fact, all the eigenvectors. And well, that's it. So any questions about that? I have a question, please.
I noticed that you just use the plus minus I over two, right? And plus minus one over two square root of three. But why you don't write plus and minus one over two in when m is equal to one? I don't know.
But it's not a solution of the beta equation.
So it's different solution.
Yeah. So, yeah.
Okay.
So, yeah, very good. So the point is that for a given value of L, okay, so here like L equals 4, then I fix M, it's like M equals 2. Then I have this equation. For M equals 1, I have different equation. So we'll have different solutions.
Yeah, I know that, but can you just push forward the slide? I want to see.
Forward.
Yeah. And forward. Yeah, because I'm curious about the sum of the degeneracy. Because if you combine combine m equal to 1 case, that we don't have the sum of the degeneracy is 16. I mean.
I'm not catching your question.
Like, why aren't there two solutions, one being I over 2 and the other being minus I over 2?
I know, but so for M equals 2, we have 2 beta roots. So we have to solve for both of them. So one of them is plus I over 2, another one is minus. But right, because the equation is 2 unknowns. So like U1 and U2.
The number of variables is equal to m.
Yes, number of variables is M. So we have M equations for M unknowns. So yeah, so here this J runs from 1 to M. So that's so Kj, the number of unknowns, or Uj is M. So we have M equations for M unknowns. So that clarifies?
Yeah, I understand.
Okay, yeah, thank you. Other comments or questions? So, yeah, so it's not so easy to solve these equations, so we'll come back to that at the end. But if you can solve them, then you're in business, at least for what I've said. Yeah, so now I'd like to say a little bit about how one could try to prepare these states on a quantum computer. So here I slightly generalized the model and I put a factor of delta. So before I was looking at delta equals 1, but you can choose other values of this parameter. So the game we want to play is, suppose we know the beta roots, K1 to Km. That's a big ask, but let's suppose we know them. Then the question is, how could you prepare the corresponding beta state? So actually, several groups have been looking into this question. So the Virginia Tech group back in 2021 found an algorithm based on this coordinate beta ansatz that I just described. In fact, the first step of that algorithm is to prepare Dicke state. So that's how I got introduced to Dicke states, by trying to understand their algorithm. And but their algorithm is probabilistic. And in fact, if you compute the success probability, turns out to be, goes to 0 super exponentially with M. So it's a problem if M is large. Also, it involves, using ancillas, and also it's limited to beta roots K that are real. Then following year, a group in Madrid looked at this, and they used a different scheme, which I haven't described, called algebraic beta ansatz, also very beautiful. Their algorithm was deterministic, but it involved QR decompositions, which had to be done classically. And then the following year, again, the Madrid group came with a sort of hybrid approach, algebraic coordinate beta ansatz approach, where they proposed an analytic formula for the unitaries and their circuit. But the circuit itself, in terms of gates, is not yet explicit. And so today, I'd like to show you another way, which is based on the coordinate beta ansatz, which is deterministic. It doesn't involve ancillas or QR decompositions, and it's the circuit is quite explicit. So so let's write the beta state now in this way. So here, this is the sum over all permutations of M1s and L minus M zeros. So for example, for B42, we have 2 1s and 4 qubits. So it's like the Dicke state, except we have some coefficients in front. If I put all the F's to 1, this would be my Dicke state D42. And these coefficients are given by the formula I showed you a few slides ago, coming from coordinate beta ansatz, which depends on these beta roots. And these X's here are the positions of the ones in these W's. So the point is that these coefficients, and there's L choose M of them, they're known. And so, job is how to prepare this. And for a given beta state, it's going to be important to define this quantity here, psi of B, defined here. So what this means is I'm summing over all permutations of the form AB. So they end in B. So in other words, if I can write W is tensor product A with B, then those are the ones I include in the sum with the right coefficient. So I think that I call this the B tail of the beta state because it ends in B. And F of B is just a normalization, so that makes sure this guy is correctly normalized. So for example, this B42 I showed you on the previous slide, you notice that all of these guys end in 0. So the 0 tail of this guy is given just by the sum of these 3 terms correctly normalized. In particular, if my tail is the empty set, then I get the whole beta state, BLM. And the main idea, like we did in the Dicke state, is do recursion, but now we're going to do recursion over the length of this, over the length of the tail. So I'm going to define an operator which prepares the tail from a simple product state. So this is called the beta operator. Again, it should be unitary, and I want it to be independent of the tail, B, and also L. In particular, as I said, when B, the tail is empty, I get the whole beta state. And so then I have a unitary which maps this product state into the beta state. And so this is the thing we're looking for. And the recursion is very simple. It's just here, which is says that, well, if it ends in B, actually it must end in either 0B or 1B. Kind of obvious. And G here are just a ratio of these F's. So for example, in the previous slide, I showed you that for this B42, I had this 0 tail. So these guys end in 0, 0, and both of these end in 0, 0, 1. So I can split these up like this. And this is going to be my psi 0, 0, and this is my psi 0. And so indeed, psi 0 is related to these. So so my recursion in the length, here the length of B was 1, here the length of B is 2. And so now I'm going to plug this guy into both sides here to get a recursion for this UM. There it is. And so then I can telescope and I get UL in terms of these W's. And so it suffices to construct the W's. And then again, I'm going to look for some simpler operators which perform the job of W. I'm going to have to go a little fast now, I'm sorry, but it's similar to what you've seen before. So W in terms of these I's, order product. So it suffices to construct the I's. And then this is the circuit. So generalization of the one we saw before, but now this operator here is a product of rotations, where it's product over all possible tails, B's, for given values of M and L. And this rotation involves, is the general 1-qubit rotation, where the angles are in terms of these coefficients G, which depend on the tail B. And what this means is that I have controls. These are just controls where the B's, the tails, have ones. And that's it. So these are all the ingredients in the unitary. So for example, in the case of 4-2, this is the full circuit.
Sorry, all these angles in the previous slide, you would pre-compute them from these Bethe rules?
Yes, exactly. Yes.
Related question to this. So do you know actually if you change these angles, if they are not the angles corresponding to the Bethe solutions, how many actually, because the form of the state you written, so with say two excitations, two spin up. So the expression you had was generic. It was a state which was composed of all those basis states with two excitations, but with some coefficient. Now, by tuning these angles, can you actually achieve arbitrary such coefficients, or?
Or I don't know, but
Because then it would be like the same protocol, but not for preparation of Bethe states, but for preparation of, say, arbitrary state of that form.
right.
Which is even more powerful.
Yeah, I should think. It's, yeah, I don't know. But no, no. So in fact, no, I know. So for any F, any set of Fs, yeah, it'll work. So yeah, so indeed, yeah, for any F, it'll work. Yeah. So so this is a circuit for 2. Again, this prepares a reference state, and then this is the W's. And this comes from the empty set, and then B is 1, B is 0, and here B is 1, 0, 0, 1. And again, these controls here differentiate between this B, the 1, 0, and 0, 1. And if you remind Dicke state, D42, it's almost the same, except here we have these extra gate here and this extra control. And also the angles are going to, if you look carefully at the angles, they're different. But the problem is, as you increase M and L, then the number of gates grows. And in fact, the circuit size is of order L choose M. And since the number of F's coefficients are L choose M, this is roughly the number of free parameters. So we expect that the circuit is more or less optimal. Yet for the worst case, when M is L over 2, this number here is 2 to the L. So it's very expensive, very expensive. So
physics, in which amps are you interested? Like, I guess you can compare any of them. Some are more expensive. Right?
yeah, no. So for small L and M, you can do it on.
So I mean, like for if you fix L and then like for which values of M, is it?
Yeah. So for example, if you look at the antiferromagnetic case, so because the Hamiltonian has a coefficient, so if you one sign is like ferromagnetic, the other one's antiferromagnetic. So the most interesting one is the antiferromagnetic, and there M is half L. So that's the worst case. Yeah. So you'd like that, and maybe that'll be the ground state. And then and if you look at low-lying excited states, then M will be close to half L. So it's like the worst case. So, yeah. Yeah, so I mentioned it's hard to solve the Bethe equations. And so someone from my camp will have this obvious question, can quantum computers help? So the idea we had was to try to exploit VQE, variational quantum eigensolver. So for those who don't know, this is a hybrid quantum classical algorithm, which is now very popular for estimating ground state energies. of Hamiltonian, say, quantum chemistry, using the variational theorem. So the idea is you start with some normalized trial state, depending on some parameters, I'll call theta. And then you perform some iteration. So at the first step, you can choose these parameters. At the 0th step, choose them, say, arbitrary, and then you compute the expectation value of your Hamiltonian in this trial state. This is the quantum part of the calculation done on a quantum computer. Then on a classical computer, you can optimize, you can upgrade the parameters, and then you can just repeat. And when it converges, you can stop, and the variational theorem guarantees that the expectation value of Hamiltonian will be best greater than or equal to the exact ground state energy. And so idea is very simple. We're going to estimate beta roots using this approach, taking the exact beta states that I've described as trial states, and then using treating the beta roots as variational parameters. But to test it, we used, instead of the quantum computer, we used classical simulators. So we did this in Qiskit, and actually Qiskit has two simulators, the state vector simulator and the error simulator. So for those who don't know, the state vector simulator performs matrix arithmetic to compute exact expectation values, which is not what a real quantum computer would do. A real one would use shots, and here we're going to simulate it using noiseless simulation, using 10,000 shots, 10,000 trials. So for the ground state beta roots, just an example, we chose delta is equal to 2, and we went even values of L from 2 to 6, and so M from 1 to 3, and then this is the exact energy, and this is the true roots computed in Mathematica using Newton's method. And notice in this case, the beta roots are real. So then using this VQE approach, using the state vector simulator, the results are almost the same for the beta roots, so it worked very well. Using the using shots, using the air, the results are not as good, but still fairly good, agreement with the true roots. And then for excited states, instead of minimizing the Hamiltonian, what we did is we minimized the variance of the Hamiltonian. So the variance of the Hamiltonian is this, right? This is an idea used recently by this group. So the variance should be 0 for exact eigenstates. And again, for the closed chain, for delta equals 2, of course, there's many excited states, and these is just, I chose just some examples. So now the true roots are not necessarily real. We have some complex ones here. For example, here M equals 3. So we have 3 beta roots, 2 are complex and 1 is real. So using this VQE approach with the state vector, again, almost the same. So very good. With the error simulator with 10,000 shots, again, fair agreement. You can improve the agreement if you increase the number of shots. Okay, so to conclude, I've described a deterministic algorithm for preparing exact beta states. Actually, so your question, so it works actually for any U1 eigenstate, not just beta states. And we used it in a VQE setup to estimate beta roots. But I have to emphasize that this circuit is expensive, both classically and quantum. On the classical side, these coefficients F involve sum over permutations, and the number of those is like n factorial. So expensive to compute the coefficients classically, and then on the circuit itself also has a large circuit size and circuit depth. So we didn't really exploit integrability in this approach, except for the formulas for the coefficients, these functions F. So it would be interesting if one could find an algorithm that does exploit integrability, maybe you could at least decrease the classical cost. And it would be really nice if you could also decrease the quantum cost as well. Maybe one way is using this way exploited, for example, here, using intermediate measurements and feed-forward operations that they use for Dicke states. And also here, we limit ourselves to spin a half, but there's also integrable models using for higher spin magnets and also for higher rank magnets. So one could try to do that. And here our models had U1 symmetry. You could even try to be bold and go beyond models without U1 symmetry. There's many other questions, but I'll stop here.